Hi! Today's lecture is going to be a continuation from our last, where we started talking about how to write chemical reactions. Today's focus is going to be the last step. How do we balance them? How do we write a chemical equation so that the atoms of our reactants and the atoms of our product are going to be equal in number and type? So sort of thinking back to where we were last class, we know that every chemical reaction will have reactants on the left-hand side and products on the right-hand side. The reactants are our starting materials and the products are our ending materials. In the reactants, that's where we'll find the bonds holding the atoms together will be broken. And on the product side, after the atoms or ions, again, my apologies, rearrange, then new bonds are going to form. We learned a bunch of symbols that we use in our understanding of how to represent these chemical reactions on paper. And we practiced explicitly starting from a word equation, which is only using sentences to describe the reaction, and translating them into formulas, which still isn't what chemists want because they're not telling us how much. So again, it's like going into the kitchen and being told first in words what the ingredients are for brownies. And then all we've done was then translated those ingredients into what their chemical formulas are. We still haven't quantized things. I haven't said, well, how many eggs, how much sugar, how much cocoa powder, and that how much part comes from the balanced chemical equation. So let's start our notes from there. The balanced chemical equation, and remember that word balanced is not always there. Whenever you see chemical equation, you know that means balanced. And we had said that this upholds the law of conservation of matter. The law of conservation of matter. The law of conservation of matter states that matter is neither created nor destroyed in any chemical process. Matter is neither created nor destroyed in any chemical process. The law of conservation of matter states that matter is neither created nor destroyed in any chemical process. In other words, the matter at the start is equal to the matter at the end. The matter at the start is equal to the matter at the end. Let's look back at the two reactions we had done last class. We had solid sodium reacting with gaseous chlorine to produce solid sodium chloride. That was our first one. And we had said that perhaps you're able to look at this, and note that the matter we start with and the matter we end with are not the same. Well, first things first. The yield sign is dividing what we're starting with versus what we're ending with, right? Reactants are what we start with, and products are what we end with. We have one sodium atom on the reactant side and two chlorine atoms on the reactant side. When we compare that with what we've got on the product side, one sodium and one chlorine, we'll notice that those quantities are not balanced. Matter is not conserved. So the way we go about balancing it is by going to the side that needs more of something. And you'll notice that I've sort of locked in the atoms of our molecules or our compounds by putting them in this bubble. The only way that I can get more atoms is to add more of the bubble that it's in. The chlorine atoms are the ones that are out of whack. I've got 2 chlorines on the reactant side and only 1 on the product side. I need more chlorines on the product side. Chlorine exists in this bubble where not only is there chlorine, there's also sodium. So by adding another bubble of sodium chloride, now my chlorines are balanced. However, my sodiums are out of whack. So now I go back to my reactant side and balance out my sodiums. Again, sodium, you need to add a bubble. In this instance, the only atom in the bubble is that of sodium. So when I look visually now, I start with 2 sodium atoms, end with 2 sodium atoms, start with 2 chlorine atoms, end with 2 chlorine atoms. Everything is balanced. The matter that I start with, the matter that I end with are equal in type and in number. That is the balanced chemical reaction. My final step in terms of writing my answer is I now need to put a coefficient in front of any of the symbols where I needed more than 1. I needed 2 sodium bubbles to balance this out. Only 1 chlorine, so just like in math class, if you have only 1 X, you just write an X. It's understood that you need 1, otherwise why would you bother writing it? And in front of the sodium chloride, I would need the number 2. Note when I say this is now a balanced reaction, it does not mean that I'm summing up the coefficients, right? 2 plus 1 is 3. And then there's 2 on the product side. That's not balanced because that's not what I'm balancing. I'm trying to balance the atoms that are involved in this chemical reaction. And I say that loosely. I know that sodium chloride is really ions. It's just easier to say atoms when I'm talking about balancing. Let's try the next example we did together. The second example we did together was the formation of water. We had hydrogen gas reacting with oxygen gas to produce, when heated, dihydrogen monoxide vapor, or gas. Okay, we want to balance this reaction. You'll notice again the first thing I did with my scrap work was I divided this. I separated my starting from my ending materials. Then I went to each of my formulas and I sort of literally wrote out H2. I have 2 H's and I locked it in a bubble. The next formula says O2. I have 2 O's, locking it in a bubble. My formula says H2O. 1 H, 2 H's, and an O. Lock it in a bubble. Once my bubbles are locked, now I deal with looking at 1 atom at a time. The first atom from the left is hydrogen. There are 2 on the reactant side and 2 on the product side. That's balanced. Bravo. Move to the next element. The next element is oxygen. There are 2 atoms on the reactant side, 1 atom on the product side. That is not balanced. The product side needs more oxygen atoms. The only way I can get another oxygen atom is to add the whole bubble. I can't just throw one in here because now that formula is H2O2 and no. The formula is H2O. You cannot just add atoms randomly. The only thing you can add is another bubble that has that atom along with whatever else is in that bubble. So now my oxygen atoms are balanced, but I've thrown my hydrogens out of whack. Now I'm ending with 4 hydrogen atoms and starting with 2. So the reactant side needs more hydrogens. The only way to get more of something is to add a more bubble along with whatever is in it. And it just so happens that I now have 4 hydrogen atoms to start with, 4 hydrogen atoms to end with, 2 oxygen atoms on the reactant side, 2 oxygen atoms on the product side. My matter is now balanced. The law of conservation of matter is now upheld. So I finalized my results by counting. How many molecules of hydrogen did I need? 2. How many oxygens did I need? 1. I don't have to write it if I don't want to. And how many water molecules were produced? 2. So seeing that 2 hydrogen gas plus oxygen gas produces, when heated, 2 moles of water vapor. This answer, as I have it now written in the red ink, highlighted in yellow, that is the chemical equation. This is the one that is so important to chemists. Just like a recipe to chefs, the one that has the quantities is most important to them. This highlighted version is the most important one to chemists, because now those coefficients are telling the quantities. That's like saying 2 cups of hydrogen and 1 cup of oxygen will make 2 cups of water. But instead of cups, in chemistry, we always count them in moles. You could, at the particle level, again, still talk about these individual molecules, but remember, those are so small that we're not able to count them. So that's why we go to the moles unit. I look forward to giving you an opportunity to practice balancing equations.